So today we have Nirmalya from Mandi. He'll give a talk on HKLL in deSitter. He did his PhD from Math Science, and thereafter he was doing postdoc in IT Madras, CMI, and IACS. And after that he joined as an assistant professor in IT Mandi. And so he will just talk about this. So.
Yeah, thank you, Gaurav, and thanks for the invitation. It's good to be here again. For those who were at the last talk, I must start by reassuring you there will be nothing controversial in this talk. The only controversial thing I have is the idea of maybe deSitter holography. Okay, so this is based on work done with my student Arundhati. And so this is the summary of what I'm going to talk about. So for those who know HKLL and deSitter, the work is basically what it says on the tin. It's HKLL in deSitter. The idea of HKLL is the motivation is to, in case of ADS holography, the motivation is to complete the bulk boundary dictionary. It's a translation job where you want to translate your bulk physics into your boundary physics. And so you want to translate your fields, bulk fields, to some boundary objects, some boundary observables, so that you can ask questions about the bulk from the boundary. So that's the kind of translation one wants to do here. And this phi zx that you see here, this is a CFT operator. This is an operator in the boundary conformal field theory. These O's are primary operators on the boundary conformal field theory, and this is smeared over these boundary operators to give something whose correlation functions replicate exactly the correlation functions of the bulk field phi zx. So this is I will talk about this in more details, but the HKLL construction is about constructing such boundary representations of bulk fields. And so what we want to do in this, what we have done in this project is do this kind of thing for deSitter. So we don't know if there is a CFT corresponding to deSitter, but we assume that there is, and if there is, how would we translate bulk fields in deSitter to operators on the boundary. So that's the project we do. There is earlier work on this, but that is restricted to this heavy scalars or principal series scalars on deSitter. And the new result that we have is when we construct this for all masses, scalars of all masses, and also integer spins in deSitter, we get that for some cases this smearing function k that appears here is not an analytic function, it is some distributional nature. And this is something that, let me just finish. This is something that's also seen not in pure ADS, but in the case of ADS black holes. So we don't need this k smearing function to be a function, it can be a distribution, because we will only calculate 2-point functions with it. But it turns out for ADS black holes also this can be distributional. And that is the result that we also seem to be getting for pure TS. For some ranges of mass spin intervals. Yes, please.
You want it to be a function,
Huh?
it can't be a distribution.
Sorry?
You say it cannot be a distribution, it has to be a function.
So in pure ADS, the result we know is that it's not a distribution, it's a function. But here we are getting that for certain ranges of mass spin and dimension, it can't be written as an analytic function, it becomes a distribution. And that is something that's also true in ADS black holes. So if you have a black hole in the anti-deSitter space, then we know that it absolutely cannot be analytic. There are divergences in the smearing function, and it has a distributional nature. Here it is a little bit better because we can still write some. I mean, there are still known expressions in the mathematical literature of this kind of thing, which are distributional. Yes? Operator O is an operator, yeah. So this is an operator in the boundary conformal field theory. This is also an operator in the boundary conformal field theory. Now, yes, they're all both in the future. So this expression is for ADS, but in DS they will be in the same time slice. Okay.
So boundary means taking z to 0.
Here boundary, yeah, in ADS
so
boundary is
why does phi depend on z?
Yeah, so I will come to this. Why does phi depend on z? Because phi is a boundary operator. This z and x have to be considered as some labels. So you can see why phi depends on z, right? Because this is smeared over some k function, and this function has the zx. So it is this O weighed by some smearing function, which is labeled by the bulk coordinates. And so ultimately this will kind of mimic a bulk field in ways that we will discuss. Okay, so this is the summary. So any questions?
Who is the CFT operator?
Who is the CFT operator?
And phi is the bar.
Phi is also a CFT operator, which is called a boundary representation of a bulk field phi. So I will discuss this. I will introduce this in more details.
Distribution in what variable? K.
I will tell you when we get there. Okay, this is for ADS. So when we get to the deSitter, I will tell you. Okay, so this is the outline of the talk. I will start by introducing the idea of boundary representation in ADS, talk a little bit about DSCFT, and then tell you the results on boundary representation deSitter. So these two parts are slightly more pedagogical, and this is like the results that people have done. Okay, so ADS-CFT, there's a ADS-CFT duality, and we have an ADS, anti-deSitter space, and in the boundary of that anti-deSitter space, it's flat, and some conformal field theory lives on that boundary. And so there's a correspondence between these two theories. So Zx are the coordinates of the anti-deSitter space, and just x is the boundary coordinate. So z is the radial coordinate, and z goes to 0 is the boundary. So what happens is, if you take a bulk correlation function like this, and if you take it to the z goes to 0 limit, boundary limit, while also scaling it appropriately, where this delta is the conformal dimension of this CFT operator. So when you do this, you will find that you end up with, this is what ADS-CFT is telling us, that if you do this, you will always end up with a correlation function in the boundary conformal field theory. This is a result from ADS-CFT correspondence that's called the extrapolate dictionary. And so what we want to do here is we want to understand the bulk physics from the boundary. And this is not enough for that, right? Because this is telling you that if I take bulk correlation functions and take some particular limit, I get boundary correlation functions. Now what we have in our hands is this right hand side, the boundary correlation functions, and we want to know all the bulk correlators from it. This is not giving us that. This is only giving us that in some limit. So what we want to construct are these phi CFTs. So some boundary operator, which I am calling phi CFT, which is labeled by some bulk points, and if I take this left hand correlation function in the CFT, so this 0 is the vacuum state of the CFT, do this whole thing in the CFT, then that should reproduce the bulk correlation function of the field phi. Okay, so the left hand side is in the correlation function in the CFT, right hand side is in the bulk, and we want to construct such operators phi CFT, which exactly mimic my bulk fields, and that is called a boundary representation. So this phi CFT is the boundary representation of the bulk field phi. So how?
Agnostic about the space-time signature here.
We will work in Lorentzian signature. So this Z label is the bulk label, and it does not have any interpretation in CFT. So in the next slide, you will see where this Z comes from.
So for the CFT phi's, the z's are different, and while in the first equation the z are all equal, and we're taking all z to 0.
Yeah.
Okay, that's the difference of z.
Yeah, because you want to take all of them to 0.
So what does small n stand for?
Small x,
Small n.
or the number of this guys. So there are n of them. So if you have 2 of them, it will be 2 delta. Okay, so let's do this. So how does one find this phi CFTs? So the idea is that the phi CFT should satisfy this equation. Basically, the phi CFT should have a dependence on this coordinate labels z and x, which is exactly the same as the bulk field phi. So it should satisfy the Klein-Gordon equation. We're doing it for a free scalar. And we take this extrapolate dictionary that we had here as a boundary condition, because within correlation functions, if you look at this, within correlation functions, this is true. Okay, this is how these things behave. So we are taking this as we take this, not we, this has been done 20 years ago, take this as a boundary condition. So this whole problem now becomes a boundary value problem, where you have a differential equation and you have a boundary condition. So we combine these two to solve for phi CFT. And this is what is called the HKLL construction. And this was done by first these people, and then this HKLL did it in for all kinds of fields, and it's known after these 4 people: Hamilton, Cabot, Lipschitz, and Lowe.
Will there be an N here next question?
Where? Oh, sorry, this N is a typo. Yeah, thank you.
So,
Yes.
this representation, is this an ansatz or does it have any more information?
This one? No, this is not an answer. So when you solve this, you get a solution of this form, and I will have to show you K to get the full answer. So when you take this and you solve this, you get something like this. But this should not be too surprising. This looks like a green function type thing where you have specified the boundary condition and you have some smeared over some green function type thing, right? So, so this is the kind of form you will get. And what is? Yeah. Yeah. So phi CFT is the boundary representation of a bulk field. Phi CFT has to satisfy this. This is the defining condition for phi CFT. So phi CFT is an operator in the boundary field theory whose correlation functions reproduce the correlation functions of the bulk scalar.
So the boundary condition is in the correlators, or is it?
Boundary condition is, sorry, what is the question?
Boundary condition is in the correlators, like the extrapolate dictionary was defined for the correlators.
Yeah, so extrapolate dictionary was defined for the correlators, and that we are taking as a boundary condition, because when we shift this back, that calculation will be within correlators. So when we take a phi CFT like this and we substitute it back in here, we will get the same result. So by construction, this will, so what we will do now, if you want to check if this is the right answer, we will take a correlator, CFT correlator, and then OO correlator we already know, right, because it's a CFT and 2-point function we already know, and then we just have to integrate over this case and get some answer, and that answer will be exactly the same as what you would have gotten from bulk.
So this extrapolation equation, so
Yes.
is that true only in a weak sense, like inside the correlator?
Yeah, it is true.
Only in weak sense?
Yeah. But now this is phi CFT, so this is the boundary operator. So we want to impose this condition on the boundary operator. Okay. So of course we have to find K. So the problem reduces to finding this smearing function K. And there are like 7-8 different ways of finding the smearing function or finding the boundary representation. And most of them were done by this original people HKLL. So let me just go through a few of them. One is called the mode sum approach, but this is simply just solving this equation by taking a Fourier expansion. So you Fourier expand phi CFT, do usual thing, put the boundary condition, just the most usual way of doing a differential equation, and then you get a result like this. Okay? And these F's are the mode solution. So in ADS you have normalizable modes and non-normalizable modes. Only the normalizable modes are kept. And so if you know this mode solutions, then you know the smearing function. So the only information input that you need to construct the smearing functions, you can see, are the mode solution. The CKs also come from some limit of the mode functions. So the only thing you need to know are these modes. There's also a green function approach where you use the green theorem, which is this, construct some green function and then find it. Okay, so different ways of solving differential equation only. And there's also a symmetries approach by these people, where the idea is that this boundary representation, which is a boundary operator, how does it transform under conformal symmetries of the boundary, and then you demand that these ones transform under conformal symmetry of the boundary in the same way as a bulk field would transform under bulk isometry. So these J's are boundary conformal symmetries and these guys are bulk isometries. So there has to be a consistency, because this is mimicking a bulk field which will also transform in the same way. And so by demanding that and also equations of motion, you can fix this phi.
So you,
Yeah.
in that case, you only need the equations of motion.
Yes.
In this case, you seem to require both water.
Yeah. So you can not water in just this commutation relations is enough. If you do it this way, then you can check. You can do the other thing. You can check that these also satisfy the symmetries. And if you do it this way, you can go pretty far without having to impose the boundary conditions. But eventually you do, have to impose the equations of motion. But eventually you do, and then you get the same phi safety in both cases. So the result you get is the same in both cases.
But why should what follows from that, Sukuri Nakayama thing, give you a two-derivative equation of motion for phi safety?
So because you have something, I mean, because the Laplacian is the one that commutes with all the generators, right? Because that is this thing. It's the Laplace Beltrami, whatever thing. Okay. So yeah, so this is the picture that you get. So this is in ADS2. So what you get is the smearing function is supported only on the points which are space-like separated from the bulk point under consideration. So if you are taking this phi of x, if you are reconstructing the field at x, you are finding boundary representation, then this k, smearing function k that you have, will be non-zero only on points which are space-like separated from this point x. So for x it will be like this, for y the support is like this. So smearing function is non-zero only for space. This is a fact about smearing functions. Okay. So this is all about HKLL, and now we want to go into deSitter. Okay. Yes, sure.
Not the other side, left side, x.
So this is ADS2. So in ADS2 you can choose this thing to be on either side. You can use any of the boundaries. So you could choose it to be this one, or you could choose it to be here. Similarly for y. For higher dimension you don't have that choice, because now there's a rotation here. So all the points which are space-like separated. So it's like this, and also points like this. So all around there will be. I mean, you have to rotate the support. So you get all those points. Okay. So now we have deSitter space-time. So we will work in the flat slicing. So deSitter space-time kind of looks like rotated ADS, and it does not have space-like at spatial infinity. There are no boundaries. These are poles, and the boundaries are at yes.
Is this support in time?
In this case, yes. So it is ADS2. In general, it will be on both space and time. It will be on all the boundary coordinates, but it has to be space-like separated in the bulk from the bulk coordinates. So all the boundary points space-like separated. So of course there will be time also. Yes. So this is what deSitter looks like, and these are the boundaries. And in this coordinate system that we are considering, this is eta is equal to 0 is the boundary of deSitter. So this is like your Poincaré patch, but rotated, and eta is like z. So like z is equal to 0 was the boundary, now eta is equal to 0. Okay, so now we want to do, now let's consider a little bit about DS safety. So if I take a bulk field in deSitter, let's take a scalar field, and let's look at how it behaves near the boundary. So in case, so this kind of fall off is similar to ADS, except that instead of z you have this eta, which is time, and you have this, so you can write a field near the boundary like this, okay, and O's deltas, don't mind those deltas right now, they are just coefficients of this, and delta is this guy. Now in deSitter you get different possible deltas, okay, so there are some classification of deltas. So
What was H here?
H, where is H? Oh, this is the Hubble constant. Yeah, sorry. So this is H here is the Hubble constant. We'll put it to 1 later. Okay, so this, depending on the allowed values of delta, there are 3 different unitary representations of a scale of SOD1 that acts on this on the scalar fields in deSitter. So there's a principal series, which is our heavy mass, where this is this, the mass is heavy, and this guys have delta equal to, it can be complex. So delta is complex here. And then you have the complementary series or light scalars. I've written something wrong here anyway. And here you have delta in this range. And then you have this exception series, which we don't want to talk about. Yes.
Is all of this only true for scalars?
Yeah. So this particular classification, this kind of classification is true for scalars. For
Actual HKLL, the description.
sorry.
If I had to do stress tensors,
No, you're asking about HKLL or deSitter? Now I'm
Not-
just looking
not
at
deSitter,
fields in
deSitter.
okay, HKLL. Yeah,
Could you have gravity in the bulk?
we
and
can
use
have
this?
anything. I mean, this HKLL, this smearing function has been constructed for gauge fields, gravity, scalars, fermions, you name it.
Then
Perturbatively, of
in
course.
the gravitational theory, how
Yeah.
do you define this space-like separation?
Yeah, so in the gravitation, I mean, you're doing it perturbatively. And what you want to construct there is not like a field phi, but something that is diffeomorphism invariant, so something like a geodesic coming to the point. So these points will be now labeled by some geodesic distance from the bulk, and you can do the same thing.
So you mean on the boundary there are 2 points and the geodesic connecting them, you label them by that?
No, so take some boundary point, take some geodesic to that wherever you want to be, and the geodesic length will tell you like will label that point, and that thing is a diffuse invariant observable because the boundary doesn't move under small diffuse. Okay, so we have this series of scalars, and so now if you look at the isometries of deSitter, and if you take them to the, so you write all the bulk isometries of deSitter, they form some SOD1 algebra, and if you take the limit to eta goes to 0 to the boundary, I have not written it, but you will see that the action of those generators is exactly the same as the action of conformal symmetries on a plane. So it's some Euclidean plane acting with some conformal symmetries SOD1 at eta is equal to 0. And this, guys, of course, this phi transforms under the bulk isometries of deSitter. And how does it transform when we take this eta goes to 0 limit? They transform this O delta and OD minus delta transform exactly as conformal primaries of d dimensions, 1 delta and d minus delta. But this is a kind of Euclidean. Delta d minus delta. I mean, the transformation is this. And so people have conjectured for a long time that there may be some ds-CFT duality where the scalar field, for example, is dual to these 2 operators in the conformal field theory, and there's probably some duality between the bulk here and the boundary at the future boundary or past boundary.
But the geodesics in DS do not return to the same boundary, right? They pass to the past infinity from the future.
Yeah, so the boundary thing was for the gravitational field. So if you want to reconstruct the gravitational field in a diffuse invariant way, you want to construct. So for deSitter, of course, there's the whole question of all points not being connected with geodesics and so on, but we are not doing gravity on deSitter. So yeah, so we will just be doing scalars on deSitter or gravitons, but not in a diffuse invariant way at large n. Yes.
So at this point, this is all kinematic, right? It's just symmetries.
Everything is no. I mean, if you want to do this, you have to use this right. This equation of motion you have to use.
In the deSitter case,
Yes.
when you say that it's dual to O delta and OD minus delta,
Right.
this comes from symmetries.
This comes from symmetries. This is a fact about symmetry. So yes.
At this point, there is no reason to be like, is there a ds-CFT duality?
No. There is in fact.
This was always known just from the symmetries.
Yes. There is no. I mean, if there's a ds-CFT duality, this kind of matches up. This is consistent with the possibility of a ds-CFT duality. If it was not there, then of course you would say that maybe
Basically,
there's.
you want symmetries.
Yeah. So at least you want symmetries. But the question is, we don't know if there's a ds-CFT duality. There's no microscopic thing coming from description of those CFTs. We don't know anything about this CFT basically. I mean, it doesn't have to be unitary, it doesn't have to be local. So we don't have any knowledge of what kind of CFT could possibly be dual to ds. However, for the purpose of, I mean, for this talk, I'm going to assume that there is a ds-CFT duality, and it is worthwhile to do a bulk reconstruction where I write the bulk field in terms of this boundary operator. So, and if there is a ds-CFT duality, then it will be useful. This kind of representation will be useful. So that is the game. Okay, so just summarizing the difference. Here CFT is on some Euclidean boundary at time like infinity. In ADS, this is ADS and this is DS. This is of course at space goes to 0. Now we have 2 boundary operators dual to a bulk field, because both these modes now are normalizable, unlike in ADS where only one of the modes was normalizable. So this is a single thing. This is not needed. Okay, so this was kind of the review of the old stuff, pedagogical stuff, and now we will continue with the boundary representation of a scalar field in deSitter. So before that, if you have any questions, let me pause. Let me pause for questions. Hmm. Yes. I mean, so that then you don't have any kind of restrictions on delta. So unitarity will tell you that delta has to be positive or something. We don't have. I mean, you can already see this is complex. There is some complex number for principles.
So the fact that you need two operators,
Huh.
that's coming from symmetry.
The fact that we need two operators is coming from the fact now there are two normalizable modes. Both modes are normalizable. None of them are non-normalizable. And therefore, the fall-off has both of these. So if you want to reconstruct this guy, you have to take into account both of these modes. And when we do boundary representation, we can see that to have this as causal, if we want the boundary representation to be causal, then we need these two modes. Because they are like the positive and negative frequency in quantum field theory. So you need both contributions. We will see this. We will see this.
Both are normalizable because in the scaling dimension we have an iota, presence of iota. Is that the reason or something?
I mean, you have to remember that these are fall-offs in time. So when you normalize, you are normalizing in space. So these two both are normalizable modes. Yeah. Okay. So let's do this. So what we want is we have these two different fall-offs, and so we call these fields with different fall-offs as phi delta and phi d minus delta. And we want to find HKLL. We want to do HKLL for both these things. So we'll find a smearing function corresponding to this guy and a smearing function corresponding to this guy. So that is the aim. And what has been done before? So this was first attempted this problem by Xiao in 2014, and he used the green function method that I showed and obtained these results. Okay? But his method was he assumed that m square is d. So now I put Hubble constant as 1. So these are the principal series scalars. So he has did it only for this range of mass. And these were his results. And you can see this theta function sitting here, which are telling you that there are that this is only non-zero for time-like separations, as I will show. But you can also see, if you look at this gamma functions over here, that there are some divergences for certain values of delta and d. So for example, when gamma function has a 0 or a negative value, for example over here, then you will see that this thing diverges. And similarly here also, the denominators, when they go to 0 or negative, they diverge. And I will show you where, or example of where that comes. But so this is the picture. It is only supported on time-like points. So on the boundary points which are time-like separated, you get the non-zero smearing function. And everywhere else this is 0. So like ADS, but now it is rotated. Okay. And so some facts about this smearing function. If you started with ADS, and if you consider two different scalar fields, one with corresponding conformal dimension delta and d minus delta, and took their smearing functions and weak rotated them, as one does from going from ADS to DS, where you weak rotate the time and also the ADS radius, then you would get this exact same formula. So if you started with HKLL for one field and weak rotated, you would not get it, because now you have two smearing functions. But if you consider like two fields with different conformal dimensions and take the weak rotation. So what I want to say is that these smearing functions are just weak rotated from ADS smearing functions. So that way you can directly kind of calculate the smearing functions. Okay. And these two smearing functions, you can see in this picture, they are both acausal, meaning they are supported on the future boundary. So you need future information to kind of know them. But when you add the final result that you get from adding both these together, as in here, that thing satisfies the correct green function. So that acausal part cancels out, and the final result is causal. There is no violation of causality when you work with this boundary representation. When you put this boundary representation and check that whether this is the commutators vanish at the space-like separation, yes, they do. But if you work with only one, you might see violations of causality. So you have to have both this positive frequency and negative frequency parts, as in field theory. Okay. And similar results from other approaches have been done. So again, this is you start from ADS and you cut it off somewhere, then you get what you get, smearing function, then you weak rotate, that will give you the same results. And also the symmetries approach that I talked about earlier, you can also do it, and this was very recent, this came out 1 week before our paper in May, and this was done recently. Okay. And so I was saying that there are some divergences in this, and one place you see this divergence is when you try to do some higher spin things. I mean, you can, so the idea here, you can do it for both ADS and TS when finding these boundary representations, is that you take some spin as gauge field and fix gauge in a way that you can write these field equations as a multiplet of scalars, Klein-Gordon equations with this mass. So you can make this, you can rewrite this into a set of Klein-Gordon equations, all of which have the same mass. And if you substitute this masses or the corresponding deltas, then you find that you get divergences in this smearing function. So this was one of the limitations or problems with the original results, that you get this kind of divergences. Okay. So now we will talk about our work in the last 3 slides. So let me pause for questions. Yes.
So how this mass? I didn't get the last part. How the mass is
There is no mass, so these are massless fields, but you take this equation of motion, you do a particular gauge, you go to a particular gauge, and you define some effective fields like this, and then you substitute back in the equation, you find that these phi's satisfy Klein-Gordon, all of them satisfy, so there will be mu phi's satisfying Klein-Gordon equation with this. Yeah. Yeah, okay. So if you take this mass with some corresponding delta, and that delta is s plus d minus 2, this s plus d minus 2, and now s is an integer, d is an integer, and you substitute it here, for example, and then you will see that this can become a negative integer and give you a divergence. Okay. Any other questions? Okay, so this is what we have done. We have taken the most pedestrian primitive way of doing it, the old mode sum approach, just solve Klein-Gordon equation in TS with this boundary condition. And so we mode expand like this, and then follow the mode sum approach and get this kind of situation. This is for phi delta, and similarly you can do this for phi d minus delta. You do the exact same thing. I told you that if you know the mode functions, you can find the smearing functions, and that's the same thing that's going on here. Just use the mode functions to find the smearing functions. And then, so first of all, you have to identify when you do this that you solve the Klein-Gordon equation for deSitter, and you identify the modes corresponding to the phi delta. So you have to identify which modes fall off how. So you have to figure out what is falling off as e to the power delta. So this is the delta mode corresponding to the eta to the power delta fall off, and you have to identify the mode corresponding to the d minus delta fall off. These are the two things. So for non-integer you get something else, and for integer you get something else. So this is the kind of, so these are the mode functions that will go in this calculation, that's it. And then the smearing function becomes reduces to some integral like this, where you have some kind of product of these Bessel functions, modified Bessel function, and you have this kind of some polynomial power here. So this is the kind of integration you end up with. And the reason I'm showing is that this kind of integration was well known to mathematicians. They are called Weber-Schaff-Heitlin integrals, type integrals, and there are some known results for this. What the known result for this is that these integrals only have analytic expression in this kind of parameter range. So you can go back and see that there's a d minus delta over here, which looks like the minus lambda here, and the exact same kind of integrals, but they don't always give you analytic expressions, only in some range of this. And you can get, for other ranges, a lot of people have found distributional expressions for this in different kind of, I've written this one, this corresponds to this one, but in other cases for different kind of conditions you can get different kind of distribution expressions or some asymptotic series type things. So when you plug this back, the final result that we get, so this is the final result, that in the range where solutions are analytic, then the smearing function matches those obtained by Xiao. So the same results that was gotten earlier, we get But there are certain ranges of mass and dimension which you can see in the paper. You have to calculate separately for principal series, complementary series, and so on. That then the smearing function may be distributional. The good, sort of good news is that in some cases there are distributional expressions available, although they are long and unwieldy, and I have not shown them here. There are some expressions which you can write, which can be interpreted in a distributional sense. Okay, so this is basically the result for non-integer. For integer delta, we get slightly different results, and we get this smearing function, where the functional form of this is the same as the one here. However, the good news is that this does not have the divergences that were appearing for the higher spin fields. So that divergence is not here. But the bad news is that for even dimensional spacetime, because of the sign here, where the dimension sits, this vanishes. So this smearing function seems to vanish for even dimensional spacetimes. And this is probably a kind of limitation of our method, because we also know similar things to happen in ADS. When you do this in ADS, when you try to find the smearing function in Poincare using the green function method, you see that in even dimension this also vanishes. So it seems like there is some connection to this. So in this case, one would trust probably the other methods more. I'm not sure. Okay. So to summarize, smearing functions have been constructed for scalar fields of all masses and spins, and for some values we get this kind of distribution. Previously encountered divergences go away for odd dimension, but the smearing function itself vanishes for even dimension deSitter. So this is we have done it for scalars and all this Jane integer spins. We are yet to incorporate interactions and such. So I will stop here, and thank you for your time and attention.
So in the deSitter case, how do you impose the constraint that you're calculating in the bunch Davis cycle?
Right. So I didn't talk about that. So that is that fixes the C's that we did not fix. So we can do it for Bunch Davis. That gives some particular C's. You get something like this, and we can also do it for alpha vacuum where you get this.
Right. And do you get any special behavior for some special choice of alpha?
Not that we can see directly, but yeah, we have not explored it too much.
And what is the big goal here? So this seems like something that you could have done without actually the knowledge of any deSitter CFT correspondence by just
Yeah, this is a initial value problem type situation. So yeah, we can just do it like that. Which is also the case for HKLL, where you also don't need as such ADS CFT. You can basically do it as a boundary value problem. But then the interesting thing from HKLL has been that when you have black holes and so on, HKLL fails, and then you have to find like all these different entanglement Kajuri construction and so on. And the other interesting thing has been when you limit to some kind of not the entire boundary, but some part of the boundary, then you get to see like more interesting effects, like the smearing function diverges, and all those paradoxes come into play, which then give you things like quantum error correction and so on. Because now when you try to do this in overlapping wedges, then you run into paradoxes which need some different resolution. So here we don't know. This is just the first step. We'll see what comes up.
So this was all for this holds in any dimension, or is it just
This is for any dimension. So that's why we have this odd and even dimension separately.
So in ADS we have one normalizable and one non-normalizable.
Yes.
In DS we have both the normalizable.
Yes.
So why is that there distinction? Like why the deSitter has both normalizable terms?
It has. I don't know why it has. ADS, if you solve it, you find that one of the modes blow up, but not always. It's not necessary. There are some ranges where it won't blow up. Both can be non-bilateral also. And in deSitter, of course, in principal series, you can see that because it oscillates, these are oscillatory modes, so they're not, not blowing up. Yes.
Do you think that there are
Sorry, I can't hear you.
So I'm asking
Yeah.
whether there are avenues in that construction.
Ambiguities.
Avenues.
Avenues.
And construction would
Ah.
that benefit from a perturbative computation, whatever order for the coding.
I mean, you can do, like, if you introduce interactions, you will have to do a perturbative order by order computation.
Like, are there some open-ended questions?
I mean, in deSitter, people have not done interactions. In ADS, it's done. Interactions have been computed. So there it is pretty clear, I mean, how to do it. Order by order computation is pretty clear. But in deSitter, of course, has not been done. Although whether it's, I mean, ADS also you get some kind of.
But like, how relevant these computations for the construction?
It's not very, I mean, in ADS, no one has found any particular use for this. I mean, there are these expressions. So the smearing function that I showed gets corrected order by order when you include interactions. But any particular application of this I have not seen. I mean, in principle, the fact that this exists is important, but for those particular expressions, have not found any applications yet. Maybe there can be. I mean, no one has done 1 by n square corrections in ADS also, so that could be something interesting. So it's all 1 over n, so which is like the first order in perturbation. So next order corrections where you also see the back reaction and stuff, that could be interesting, I think. But I've not seen that being done.
These outside factors in front of your key expressions over there, which equal to 0 for some choices.
Yes,
So
these guys.
if we have constructed or we have gotten those factors by demanding that key satisfies some composition rule that Green's function satisfies.
I'm not sure. It has not been. No one has done it that way. The way Xiao had done it is just using the green function and then substituting. So just using the green function in a particular limit, taking a particular limit of green function, he was able to constrain them to some kind of linear combination of two factors, and then substituting back in the Whiteman function, he fixed the linear combination. So that, like, that is for the Bunch-Davies vacuum. So that was done. But some composition rule for that, it has not been done for DS. I think then one should probably first try it for ADS and see. And I don't. I mean, there because
Pretty good sanity check, I guess.
yeah, but the thing is, these are both on the boundary, so it's not like ADS. But it's not. There's no bulk here. It's all bulk boundary.
So if you took this seriously,
Hmm.
I don't even know the ADS picture.
Hmm.
So if you took this seriously that this is a bulk bullet,
Yes.
would you study scattering in the bulk using these?
Yeah, but I mean, you want to go to some flat space limit to study scattering amplitudes or something. People have done that.
Scattering in ADS.
Yeah. So you can start with this. You can do this, and you can also take the flat space limit and get scattering, like flat space scattering. So that's also something people have done.
In ADS.
Yeah, start from ADS, calculate these things, and then.
CD you can't because they're calculating the in-in potential.
Yeah. In DS you can. DS no. Yeah. Sorry, your question was something else.
Yeah, I wanted to see the
Huh.
same thing. Could you study scattering in deSitter?
Yeah, that. As you said.
Modify the convention.
So is that the goal is like that believing that there is a
Hmm.
DSCP
Yes.
and then how it is, I mean, it's like the logic like that, how it is happening.
So if there is a DSCFT correspondence, if there's a correspondence between these bulk fields over here and these boundary operators, how do we write these bulk fields? How do we, translate this bulk physics to boundaries? So how do we translate this bulk fields in terms of some boundary
So
operator?
like we are running this case, these smearing functions.
Yes.
So if we can like study because then somehow like we can prescribe that, I mean, how that DSCFT correspondence.
No. I mean, if DSCFT exists, then these Ks are useful. But Ks cannot directly tell you. I don't think that they can tell you anything about DSCFT because DSCFT is very unconstrained. So that has to do with these O's. Ks are kind of bridge between TS and the CFT if it exists.
Is it possible to study this in a 1 over R expansion in deSitter?
1 over R expansion. I mean, I don't know. I've not thought about it. So I don't. I mean, what do you want to do? 1 over E. Do you mean 1 over eta?
About flat space. The
Huh?
radius, sorry, the deSitter radius. Like the flat space expansion.
Okay. Yeah. I mean, you should be able to do it, but.
Any more questions? We still have almost 15 minutes, but since we finished earlier, maybe that's it. So let's thank Kaju for the nice wonderful talk.